Hello, in this video we will talk about Kb and base strength for weak bases. And ultimately this is pretty analogous to Ka, except now we're doing it for a base. So what does this look like? Weak bases ionize to a limited extent in water, just like weak acids, and this is the equation that we use. So you have your weak base, in this case ammonia, NH3. With water, the base will effectively rip a proton off of the water molecule and leave you with OH. So the base accepts the proton from the water, and there you go, functions like a base. Now, if we're going to do calculations on this, which we'll see how this goes here, we do an equilibrium calculation to solve for the hydroxide concentration, because that's in this equilibrium expression here, right? So we just solve for concentration OH, and then from there we convert it to pH. And so you can either go from concentration of OH to POH, negative log, and then 14 minus the POH gives you the pH, or concentration of OH times the concentration of H0 plus equals Kw, which is 1 times 10 to the negative 14th. So you can solve for H3O plus, and then you can take negative log of that to get the pH. Either way works just as well. I personally prefer the first one, but do whichever one feels better to you. So just like all equilibria, we can write an expression for K, and we take the product concentrations, NH4 plus, OH minus, put them on the top, the reactants on the bottom, ignore the water because it's liquid and everything else is aqueous, and this is the equilibrium constant. Now, for this, we use Kb, right? So Kb shows that this is a specific equation, and it's specific to this equation. So whenever you have Kb, it means you have a weak base, that, in water, and then the weak base gets protonated, it accepts a proton, and then you have hydroxide left. So Kb means that. So we don't need to give you the equation. We can just say, hey, you got ammonia, here's Kb, go to town. And you need to know what that equation is. Now Kb is the base ionization equation because you are ionizing the base. And bigger Kb means a stronger base, just like a bigger Ka meant a stronger acid. And so, here's ammonia, here's its Kb. Sodium hydroxide, its Kb is ridiculously large, almost impossible to measure, because sodium hydroxide is a strong base. It ionizes completely in water, whereas ammonia does not, because it has a smaller Kb. So we do this generically, just like we did for acids, right? Remember, for acids, we had HA plus water goes to A minus and H3O plus. So we're doing the generic thing here, except we're using B for base. And the base with water will be protonated. So I tend to think of this that the base rips a proton off of the water molecule, and the base itself becomes positively charged. The hydroxide is left over, and that's how it works. Really, you can think of it the other way around. The water donates the proton to the base. All right. If your base is negatively charged in the first place, like say your base is the conjugate acid of something, right? So say, actually, it's going to be confusing. Let's not do this. I'm just going to call it, I don't know, I need some letter. T. Why not? And so T negative plus water would be an equilibrium with just T plus OH. Right? So whatever this is, I just made up some letter. If it starts out negatively charged, then it'll just come out neutral over here. Why did I pick the same one as temperature? I don't even know. That wasn't temperature, guys. First I was going to pick Q, then I was going to pick R, and it's like, oh, this just got to be messy. Okay, so in the formalism of conjugate acid-base pairs, right, the base is B, and then its conjugate acid is the protonated version that's positively charged. That's a pair. And then water functions as the acid, and its conjugate base is hydroxide. So again, Kb is the products over the reactants, and so we could write it just like this generically, and then you'd plug in whatever molecule you actually have for B. You can talk about pKb, which is just the negative log of Kb, and then you can do it the other way around, right? Kb is equal to 10 to the negative pKb. Just like we did for Ka, right? Except now we have a different equation that's specific to bases. You can look these up in tables, right? Here's a bunch of bases, here's their Kbs. Now we have a lot less molecular flexibility here in just the way that the science tends to work out, that most weak bases are some derivative of an amine. And so amine is basically a nitrogen atom. that has a lone pair on it. And that lone pair can accept a proton, right? Because the lone pair is used to make the bond to the H+. So that means this nitrogen can accept a lone pair, and it'll leave you with hydroxide and functions like a base. So if you notice all these molecules in this table, they all have lone pairs on them, and they're all shown. Be like, hey, look, here's the lone pair. That's where the proton goes, and it makes something positive. So let's do an example here. Let's find the pH of some weak base solution. Now, really, it makes more sense to find the pOH, and we'll actually do that along the way. It's just that we kind of picked one. Are we going to choose to talk about pH all the time or pOH all the time? Because you could, decide to talk about one or the other. But since there's so many more weak acids, we tend to use pH. All right, so we need to deal with this base and get it into pH. So we're going to use ammonia again. Here's its Kb, 25 Celsius. What's the pH of this 1 molar ammonia solution we might have? So it's icebox time. So here's the same equation, right? If Kb, then this equation. You put the initial concentrations in. And now it's easiest to think of this, right? Imagine you have 1 molar ammonia to start, and then it goes and ionizes. Really, if you're talking about the pH of 1 molar ammonia, you don't actually have 1 molar ammonia because you have a little less because some of it ionized. But we'll typically just do this. Say, imagine you start with 1 molar ammonia, then dissociate. It's easier, I think, thought-wise, and it's still completely correct. So we're going to the right because we're making ions. And so here's the equilibrium line. And then here's the form of Kb. And then we plug this into Kb just like before, right? So this is nothing new. It's just that we have a different equation up here for Kb as opposed to Ka. So same problem we had before. We need to solve for x. And generally the way to go about this is neglect x, assume that 1 minus x is just 1, and see where that takes us. So let's do that. We'll solve for x. We get this number. Now you got to check your assumption. Was that a good idea? And so 0.0042 is only a small percentage of 1, right? So you're subtracting 1 minus, less than 0.5% of itself. And so this is a perfectly fine assumption because our limit was 5%. Another way to think of this is 5% of 1 is 0.05. Our x is less than 0.05, so this is a valid assumption. If this was not a valid assumption, you have two choices. You could either solve the quadratic, or you could just keep going with the method of successive approximations and then get to x after 2 or 3 iterations per se. Maybe more, but usually only a couple. All right, but we don't need to do that here because we found x pretty straightforwardly. Now, x is the concentration of hydroxide. It's also the concentration of NH4+, but we don't need that at the moment. We care about the hydroxide. So, all right, so there's the concentration of that. And then my preference is to put this into pOH first. So you take the negative log of this, and you get pOH. And then you can find the pH by taking 14 minus pOH. And here's your answer, 11.62. So remember, a pH greater than 7 is a basic solution. So it makes sense that we take this ammonia, put it in water, and we get something greater than 7. Because it should be, because we put a base in the water. So that makes sense. Great. The other thing we should do is double check, because who knows, maybe you solved for x incorrectly. This one was pretty straightforward, but say you went through a quadratic, you definitely want to double check. You have your formula for Kb. From the previous slide, here's what the outcome was. Let's plug x into this, and then when you compute it, you get 1.77 times 10 to the negative fifth, which is pretty much 1.8. Perfect. So, moral of the story, Kb is a different equation for bases, but otherwise it functions just the same as Ka like we did before, which functions just like all of equilibrium we did before that. And now the nuance here is that you'd solve for x, which is the concentration of OH, and then you have to do this little adjustment process to find what pH is. Great, thanks for watching.